after class and fill each other in? Yeah, I don't believe that. I don't believe it. Do you share your notes? No. Not. There might be some really good notes today. Who knows? It's the fact that everybody can watch it live, right? So they're sitting in their, or is everybody sitting at home watching live now? Do you remember the COVID lectures? I had an 8 o'clock class during COVID. The reason the class was at 8 o'clock was because I wanted a particular classroom to do the class in. So we moved my normally 11 o'clock lecture to 8 o'clock for that term so that I could get the classroom I wanted. And then it was a COVID lecture and it was all online. And I said, could you please fix it and put it back at 11? And they refused. They said, no, people have scheduled it. And they, like, if you had an 8 o'clock class and it suddenly changed to 11, would you be really pissed off? I was pretty sure more people would be there live if it was at 11, even if they had a conflict. Anyways, the COVID days sucked. All right. Has anybody got anything pressing they need to talk about their project before we start? Anybody needs something critical from some other group or needs some help from me before we start? Okay. All right. So class about computer-aided manufacturing. And when we think of computer-aided manufacturing, we often think of CNC machining and CAD and CAM. And I've broadened your experience a little bit, and we've brought in the idea of ERP software and the other parts of manufacturing that need computers in order to happen well. And we've talked a little bit about robots and factory automation, right? A very little bit. And that's because at the survey I did at the beginning of the class, everybody said that's not the things they wanted to talk about. But it is kind of an important thing. And did you know that in 1969 the world changed? What happened in 1969 that changed the world? What's that? So there was a moon landing, yeah. What else? Changed everything about how modern factories operate. What's that? I thought you were pointing to you were just scratching an itch. Got it. So a guy that I was fortunate enough to meet several years ago and have, I don't know, I wouldn't call him a friend, but an acquaintance. Several meaningful conversations. He actually changed the world in 1969 and made it so that it will never be the same again. And he did it on New Year's Day, 1969, sitting at his kitchen table, hungover. And this is how he tells the story. I'm not sure it went down exactly this way because there were martinis involved in my hearing of the story. But so this guy, Dick Morley, his job, he was an industrial engineer or a factory automation engineer. He worked for a company that when you said, so we've seen these assembly lines, you've seen the videos, right? So they were using assembly lines and doing factory automation before 1969. And what they did, any electronics people in here? Anybody's ever wired something? So what do you do if you have a switch over here and you've got something that requires electricity over here, some kind of load, and let's say that this needs, I don't know, 50 amps. See, in a car maybe? You guys have wired stuff up in cars? So 50 amps, 12 volts DC. And you want to have a little toggle switch on your dashboard that turns it on. So if I just get my battery, right? What's the symbol for drawing a battery? Anybody remember? Long line, short line. And I have to does it matter how many I draw? All right, each one represents one battery. I think you're right. So if I do this, right? And I get my cheap ass switch from AutoZone over here, and I'm going to turn that thing on. What's going to happen? Yes. I'm going to close the circuit. What's going to happen? So current's going to flow, right? And I guess we get like the plus minus, right? So current's going to flow. It's going to go through my 50 amp 12 volt DC thing here. It's going to go back over here, right? Anybody ever done this? All right, what if I change it to 100 amps, 12 volts DC? The switch is going to catch on fire, right? That switch is going to melt. The cheapo little toggle switch you got from AutoZone, you flip this on, the switch is going to melt. What's the solution? Yep. Well, no, because we need to supply the current over here. So what's the solution? What do people do in this case? No. Control it separately. So we take a relay. I forget the symbol for a relay. Relay. And what the relay does is the relay connects to the battery into the thing. And the relay has got a big switch in it. Sometimes we call it a contactor instead of a relay. But the relay's got a big switch in it, and it can handle all this current going through. And it's got an apparatus over here. So this also gets current from the battery, the switch. And what happens is when we flip this switch, it tells the relay the switch is in the on position. And when the switch is in the on position, we put together our things, right? You've seen like the Frankenstein movie where they pull the lever down and the lights dim and everything. The whole town gets dark because they're using so much power, right? So it's the same thing here. When we do this relay, we're remotely controlling this high energy circuit with a low energy circuit. And so that's how all factory automation was done before 1969. You'd have, and so these relays, so let's think about a modern factory or a factory. What do you guys want to make in our factory? Let's just sort of build a factory. What do we want to make? Let's make beer, right? So let's assume that we've made beer. So let's not even make the beer. Let's assume that we've made beer, and we're going to put it in bottles, and we're going to put caps on the bottles. We're going to put labels on the bottles. Put the bottles in boxes. We're going to ship the boxes out. So that's a manufacturing thing. It's a bottling line, right? And so how many relays do you think we need? What are the processes we have to control? We're not making the bottles. We got bottles that came in. We're just filling the bottles. So just filling the bottles and putting them in boxes. What do we have to, what are the processes we have to control? Yes. All right, so we're going to control that by turning the beer faucet on. The beer faucet, that sounds fun. Turn the beer faucet on, turn the beer faucet off, right? So we need, all right, so beer faucet. We've got an on and off. When do we turn it off? So we've got a full sensor. All right, when do we turn it on? We've got a bottle sensor. So all we're doing is filling a bottle, and we've got a switch that turns on and off. We've got a sensor that tells us when it's full. We've got a sensor that tells us when the bottle's available. Then what do we do? You've all filled a bottle, right? You fill a water bottle at a water fountain all the time. It's just like a beer water fountain. What do we do next? We could cap it right now, but if we cap it right now, we're wasting precious bottle filling time, aren't we? Should we move it out of the way first before we cap it? Then we can fill the next bottle while we're capping it. So now we got a move and say we'll move to capping station. All right, so we're going to move to the capping station. And so when do we move? All right, so this has got to talk to the bottle, the bottle full sensor. When do we stop moving? Well, I think we stop moving this one when it gets to the place that it's going, right? So we've got a bottle sensor. So we stop this one when we get to the bottle sensor. And what else do we need here? So when the bottle sensor here says, ain't no bottle, then the feed mechanism, so there's a feed mechanism downstream that sends the next bottle in, right? Now, one of the ways you can do this is you could have it be continuously pushing, and you could have a gate that stops the bottle, and so it stays there until you move the gate out of the way, right? So you're continuously pushing them until the gates move out of the way, right? All right, so we've got our bottle sensor. Now what do we need to do? So we've got our bottle. So our bottle has moved through the filling up. It got to the capping station. Now what? All we did was move it to the capping station. We've got to put the cap on, right? Right. So to put the cap, who's ever put a cap on a beer bottle? Really? Nobody ever brewed beer? Oh, you should try it. Years ago, I had a student. He was a pretty smart kid. He said, when we were in high school, all my friends got fake IDs. I built a still. Smart kid. Anyway, so beer factory moved to the capping station. All right, so what's the process of bottling got to do? Or sorry, capping. What's the capping process have to do? Yes. So you gotta hold a bottle cap, and then what? We push the bottle cap down onto the bottle, and it actually crimps it around the bottle. If it's not a twist off, I bet you I think even the twist offs, they put them on that way. They push it down, and so on the manual bottle capping thing that I have, there's you balance the cap on top of the bottle, sort of balance it, and then there's a thing that comes down and it pushes down, and once it gets to a certain point, it sort of slips over the top and squishes it together. So it's got a squishy thing and a pushy down thing. Does that make sense? Now, so you've got to put the cap on the bottle, then you've got to apply pressure to seal the cap to the bottle, right? So we got to know, is the cap on the bottle? Now, this ignores that there's got to be some feed mechanism for the cap, right? Right, so we've got to have something feeding the caps in as the bottles arrive. There's a whole bunch of different ways you can design it. We're sort of visualizing a system here, right? So yeah, you could have different things moving at the same time, and you could be filling more than one bottle at the same time. You could be filling 6 bottles at the same time and capping 6 bottles at the same time to move things ahead. But if we're just looking at visualizing the system to do 1 bottle at a time through here, so we've got to have a cap sensor. Is the cap there? We've got to have a move the cap applicator into place. So move, what do we call that? Capper. Into place. Then we've got to actuate the capper. Then we've got to remove the capper, right? And so now what we've done is we've taken a bottle of beer, we've filled it up, we've put a cap on it. We've still got to wash the bottle because you're not going to get that label to stick when there's beer running down the outside of the bottle. You got to wash the bottle, you got to dry the bottle, you got to put the label on it, you got to get the bottle into a case, you got to box up the case, you got to fold the boxes before they get to the case. So just this simple process of bottling a bottle of beer, you could see might have hundreds of sensors involved, right? So you could have hundreds of sensors that are giving information back to tell the motors when to turn on, when to turn off, to tell, I mean, heck, you've just got to have indicators. You've got to tell the operators what's going on, right? If there's a fault somewhere, you've got to warn the operator that something's wrong. So there's indicator lights, all kinds of things. So you can have hundreds of different sensors just for this simple thing. Now you want to do it faster, so you're going to do 6 bottles at a time. So each one is going to have that sensor, right? And if one of them fails, we'd have that problem. So you could end up with thousands of sensors and hundreds of different motors and lights and different actuators, the things that are going to have to operate just to do the simple process of bottling beer. It was before 1969 that we had automated beer bottling plants, because Americans like to drink their beer. They like to drink it out of bottles sometimes, cans sometimes, same kind of problem, right? So in 1969, Dick Morley was sitting at his kitchen table, New Year's Day, hungover, dreading going back to work the next day. Have you ever had those moments where you like, oh, I'm glad today's a day off, but man, I don't want to go to work tomorrow, right? So he was having one of those moments. And have you ever had a great idea and had somebody tell you that if that would have worked, somebody would have done it? Yeah. So he was sitting there and he's trying to figure out there's got to be a better way. Because what they would have is you'd want to have all the controls sort of in one place so you could tell if they're on or off and all that stuff. So they have banks and banks of relays. Oh, and relays are mechanical components. Sometimes they fail. Oh, bummer. Because now, let's say this one's not working, but it doesn't like light up and say, I'm not working, right? It doesn't do that. What happens is over here, some of the bottles only get filled up halfway and then they move on. And so you got to figure out, all right, from here over to here, follow the wire back. Is it the blue one or the red one? Follow the wires back. You figure out, oh, it goes into this relay. You got to open up the panels. You got to look at everything inside. So besides these hundreds of relays, you have hundreds, maybe thousands of miles of wire going back and forth from the relays to the stuff. And his job was to design that shit. His job was to lay out all the wiring diagrams, figure out this relay is going to go here, and then be in the field and make sure that people wired it up correctly. So he didn't want to keep doing that job. And so he was sitting there. Who said transistor earlier? So he was sitting there early in that morning. I don't know how early it was. And he says, there's got to be a better way. And it's when transistors were just coming out and you could do this kind of logic, because this is just logic. Switch on, switch off, right? It's all ones and zeros. It's binary logic. And you could start to do a whole bunch of logic in a small space with transistors. And so he invented what was called the programmable logic controller. And it's probably a PLC that controls these lights the way they turn on. Probably a PLC in this box that controls how the little push button stuff work. There's definitely a PLC in every machine tool you've ever used. There's definitely PLCs controlling all factory automation in every factory you've ever seen on TV. And so he thought of it that early morning, built a business around it. It became an $8 billion industry. So Dick did okay in the end. I got to know him because his kid went here and he was on our advisory board for a while. And at any rate, let's talk about how these kind of things are programmed and controlled. So this is sort of the introduction to what is a PLC. And a PLC is just a microcomputer that serves the same function as several banks of relays. And it operates at a low voltage. They operate very fast. And they're significantly robust. So if you didn't know about PLCs and you decided that you were going to create a bottling line to bottle your beer that you're making at home, how would you control it? If you didn't know about relays, didn't know about PLCs, just based on what you know with your WPI experience, what would you have thought of first? Yep. So like a microcontroller. So like what? Arduino. Or a Raspberry. That's how they spell it, right? You know what I mean, right? And so what's good about those?
They're not super obtuse, like well documented. You can program it like language wise, right, rather than integrated circuit design. And for me, as a WPI current WPI student, that might be more accessible.
I think what these guys have that's really good is that they are cheap. They're not expensive. This is probably not true anymore, but it used to be not all Arduinos had the same pinout. Is that still true? Yeah, but I mean, like, pin 1 wasn't always the same function on all of them, depending on who you bought it from, when you bought it. Is that still a thing?
I think different people are allowed to sell the same chip, so an Arduino can technically be a different Arduino.
Yeah. So that was one thing that I thought was kind of odd. Well, as long as you're building one thing, right, and you have the documentation, it really doesn't matter if the pinout's the same as the one you had last week, right? unless you're building a lot of things. And it may not. I think it was the Arduino. It might have been the Raspberry Pi. I think they're all sort of similar in that sense. So they're very cheap. They can be pretty fast, right? So on an Arduino, how many processes? So how many switches can you do? How many things can you control at once? I/O stuff, right?
There's like multiple arguments. Like the big one, you can get 30 something.
So you get like 30 something inputs and outputs. And so with a name brand PLC, you can they go on a backplane. So you can have as many inputs and outputs as you want, basically. So you can do a lot more with the PLC there. You mentioned programming. Anybody else have experience using microcontrollers a little bit? And so you mentioned programming languages were languages that you were familiar with, right?
Yeah, and documented for educational purposes.
Yeah, there's plenty of documented training for PLC programming too. You just haven't looked at it because you haven't tried to program on PLC. And so when the program runs, then you do your debugging and stuff like that. You figure out where the problems are. Yeah. And so you can do a lot of the same things with the Arduino and the Raspberry Pi. I actually once helped design, build, and sell to an end customer a CNC machine tool that was running on an Arduino. Right, so it was a very custom CNC machine tool, very simple process. But we chose to use the Arduino instead of the PLC because to do it with the Arduino was about $3,000 cheaper. And the end customer wanted cheap. Cheap was an important thing to the end customer. If the end customer had said robust is what's important to us, we would have gone with a hardened factory automation PLC thing. The interesting thing about the PLCs, interesting thing about these PLCs is the way that the programs work. And so they're programmed in a language called ladder logic. And you can actually, when you program it on the software that you connect, to use a PC, you connect your software to the thing just like with your Arduino. The ladder logic is often a very visual programming language, and it mimics the idea of how it's wired and how a relay would work. And I think the reason for that is when they were developing it, they were taking electricians who were used to doing relays and now teaching them how to do it with PLCs, with transistors instead of relays, right? But the other thing that makes it really robust is, so we've got inputs, we've got outputs, is the speed at which that it can go through and exercise the program. And what it does, you may have, I don't know, let's say we've got 20 inputs over here and 20 outputs over here. So each input or output will have a state. Does that make sense? So it'll be a 1 or a 0, right? A 1 or a 0. And you write your program. It's basically if input, so, and then you number them, right? 1, 2, 3, 4. If input 1 is on, then switch output 1 to on. Does that make sense? Because you're doing this sort of logic, and you can do ands ors, right? So it's a simple logic language that you're going through. But what it does at the beginning of each pass, and a pass-through program will take, I don't know, 20 milliseconds, something like that. At the beginning of each pass, it checks the status of all the inputs, and it checks the status of all the outputs. And so you can say, if output 4 is on, then do this also. So you can use the status of other outputs to tell it what to do. And you have built-in timers. I feel like I'm not doing it justice here. I feel like nobody cares. Nobody seems excited about learning. How do we fix that? What's up? Somebody move their hand. What can we do to make it better? Okay. So let's see. All right. Let's be a little bit more interactive. We have an intersection. Okay, so you got a stop lane there, stop lane there, stop lane there. Right, stop lane there. This one's on the wrong side of the road. These guys are from England. And you've got a stoplight here with lights in all the directions. So 3 lights in each direction, right? Red, yellow, green. And should we put sensors here? We'll put a sensor to see if there's a car here, if there's a car here, if there's a car here. You know, there's green boxes that are next to the stoplight things. Inside there's a PLC. So let's design. So you don't need to use ladder logic to design the program. Let's design the program that controls this stoplight. So first, tell me all the inputs I need. What's an input that I need to control the stoplight? Should we label these? Yes. All right, so I need, so let's say east. Make that one east, that one west. So I've got east. I guess those are westbound cars though, right? All right, so westbound car, eastbound, northbound, yeah. I'm just going to keep writing because the squeaky sounds cool to me. So I got westbound, eastbound, northbound, southbound car sensors. What else do I have? Any other inputs? So those are outputs. We can tell what the state of them are, but we don't have to label them as inputs. Any other inputs that we need here? A lot of the streetlights around here have a ambulance beacon. Yep. Oh, walk buttons, right? So that's northeast. So pedestrians get to do inputs. Yep. We get to decide. We're the designers of the intersection. This is a whole civil engineering class about deciding this, I think. You could probably get a PhD in figuring out the correct traffic patterns. So it's any civils here? Then we just to make that shit up as we go. But right, that's a consideration we'll have when we're doing the programming. I'm just trying to see, are there any other sensors we need? Emergency sensor. Because when that ambulance is coming, you want to clear the path in front of it. And so you stop the other ones and you let the path in front of it go. Yep. The timer is a feature inside the PLC. So we're going to have a timer. I brought my own markers today because I was worried that these wouldn't work, and then these work okay. We'll have to have a timer. And that's internal to the PLC. Do we need any more inputs? I think we got it. Okay, so now what are the outputs? So, all right, so we've got 3 north-facing lights. F, I don't know why I put F. North. We got we got to control it. If we're going to put it on the post, we got to control it. Yeah, no, I get it. Right, all we're doing is one intersection. Think if we were doing the whole city. Right, and so I got west, right? As soon as I figure out a system, I can write faster. All right, so I've got those. I've also got walk signals for all those, right? This is light. We also have walk. There, I saved writing. Sort of ditto mark sideways. What else? Do we want to tell the emergency vehicle that we received its signal? Maybe we do, maybe we don't. I mean, they can usually tell when they get to the intersection. If all the cars are stopped in front of them, they know that something's broken, right? So maybe we need that, maybe we don't. All right. So now, these are all our inputs. These are all of our outputs. And we have access to a timer. We actually have access to as many timers as we want because they're virtual. They're in the code. So, right, if you had relays and you had timer relays, you'd need a different timer relay for each timing signal you needed. Here we can just program them. So that's nice. Do we need anything else to control this? Besides, we're going to need some cars and some people. Otherwise, it'll be really boring. They can just all stay red. Yep.
Should be like a normal state. There's no input any of those sensors.
I think that'll be part of figuring out what to do. Right? Some lights, you'll notice they keep changing all night long, even if there's no cars. because they're just set on timers. Some lights only change when a car comes. You might have, if you know that this is the major traffic route, you may have it default to this flow being open, right?
Assuming that because they was all right, and one car showed up like side simultaneously, how would the light decide?
That's up to the programmer. You'd have to figure out how to prioritize that. Simultaneously is kind of tough in nanosecond timescale things, right? But so if the timescale gets fine enough, one signal will be received before the other, no matter what. So I think you just take the first come first serve at that case. All right, but do we think we need any more inputs or outputs? Do people have a piece of paper? Let's get into, I don't know, 2 groups. Just divide into 2 groups, however you feel like. And each group, write out the logic steps for controlling this light. So if this or that as logic steps, okay? So think through how you're going to do this. You should probably move so the groups are closer to each other and they can communicate with each other. So this is a group and that's a group. Okay. If you make an assumption, just know what the assumption is. So if you assume that one direction has more traffic than the other, just say that. So if I'm the ambulance and I'm driving this way, I want this lane to clear. So I want them to get a green and everybody else to get a red. I mean, that's what I would want if I was the ambulance driver. I want the people that are directly in front of me to be able to get out of the way and pull over, especially if there's like a median or something, right? And I would want to have them be able to either make a right turn or pull ahead and pull over, so they're not bulked up at the intersection. But that's like a special case. We could even ignore the emergency vehicle and just get the regular pattern going, and then you could add this in. I wouldn't stress about the emergency vehicle thing. I just was thinking it was possible to have it there. Not all intersections have them. We didn't have turn signals. We didn't have separate right left turn things.
Okay, okay.
So yield to oncoming traffic on a left turn. I mean, because you could complicate it also with, well, this is a delayed green in this direction, so that people can make the left turn right away. Right. So
Yeah, but you had someone going straight across. Well, then you wait for their cars.
Okay, so
Right, so that's why they just did.
and we won't pretend we're in Europe and have the red and the yellow on at the same time, or the green and the yellow on at the same time.
I mean, if it's just showing blue lights, I'd say we don't want to.
How about like really late at night and they have like that red light, which is stop sign, but it's like caution.
Blinking red one side, blinking yellow on the other side. You're done. Call it a day.
Or just put stop signs at every.
Yeah, blinking red all around, and then just.
Well, blinking red is a stop sign, and blinking yellow is a caution. So you can be done quick. Programming done. Didn't even need all those extra light bulbs.
but you don't care about the yellow.
Heck, you only need the one light bulb half the time.
Install.
It's either on or off, right? Yeah.
We can just put blue.
Yeah. Let's just rip it out.
We make the streets one way and get rid of half the issue.
Or we just, like, get rid of-
But I think what you should do is what I asked you to do.
I think we should just go like that, and we just go around each other.
West and east. And even and like maybe like after the line or side street has been set, and it stays in the schedule. Right. So like if there's a period where there's no one on the road, that's never gonna be like the system starts like a curve come back that way, and then there's someone that's being applied at intersection, and then the system's like that way. True. Like the first time you initialize it, it's all right there. The first time. Or like
I wouldn't worry about the edge cases like the first time you turn it on.
you just like assume that the system is like in operation.
Yeah, assume steady state. You could always do a special little program for the edge case.
Yeah, maybe that's true.
Especially if it's very small.
So if you're waiting, so right now, it doesn't make sense for you to have to talk about cars. You have a, well, that's what that's yeah. My street is small, every crosswalk is not yet. They don't have it. Yeah, I think it's like when you press the button, you can put right where you were. That's why it's not right. Right. The West Street right now, that's the button.
Yeah.
I think it's when you do get but I think like this, yes.
You can decide.
So on our main street.
Are we gonna make this complicated on ourselves? So say it's simple and you have to wait for that. I don't know if you're right now. But in that case, we just. I do. Those are better. Or better. That's assuming this that we're not. But like technically the West Street pass. Like it's like you would do this. Okay. And also. You're dedicated to unless you do something. Like I think in very traffic and very That's how like you like prioritize the walks you do in terms of cycle. Well, I know it's not that. Yeah. It's not just like
You'll have something about 5 minutes. All right, I'll be right back.
Heard that everywhere else. It's a decent.
How do you know where my Actually, I didn't like our CX.
All right, so we got a plan? Is it gonna work? All right. You should get the girl that works in front of the school my daughter used to go to. That lady controlled the street. She was amazing. Whenever, like, she'd like, go on vacation or be sick or something, like the principal would go out and be the crossing guard or something. Oh, I mean, I wouldn't drive down the street during school time if she wasn't working because she was in control. Nobody moved. Oh, if you ever have kids, don't be the parent that stops in the middle of the intersection to let your kids out of the car. In the middle. And also don't be the parent that stops at the crosswalk to let your kids out of the car and then proceeds to do a U-turn in the middle of the intersection. That would never happen when she was there, though. All right, so you got a plan. Describe your plan. What's the logic state that's going to happen? You guys have a plan too? Kind of? Do you think their plan's better than yours? Yeah, I think so too. They spent more time discussing their plan than you did. I could tell. It's all right. It's just participation. It's only 80% of the grade. But my opinion is only 5% of the grade, right? All right. So what do you got? What are we going to do?
So we started off talking about this simple cases. And
Perfect. I like simple cases.
we sort of predetermined that the chances of someone landing onto the car sensors at the same time was like nearly impossible. So the queuing system would just automatically get someone first.
One signal or the other would arrive first.
Yeah. So basically, if a car went to a sensor, we agreed that
Car goes to a sensor. Okay.
opposing directions can go at the same time.
Opposing directions can go at the same time.
So if it's someone arrives at the northbound one.
So if north green, and I've labeled it output 3.
Okay.
So if output 3, output 3.
Yeah.
If output 3 is on, we also want, where's south? We also want output 6 to be on,
Yes.
right?
Yep.
So you could do a logic statement that says exactly that.
Okay.
If 3 is green, then 6 is green. Yep. Oh, you got to have that too.
Yeah. We were
Then-
getting there.
So if this is on, this has to be on.
Right.
And this has to be on. And this has to be on. Right? So if this, and this.
So we had also included that once the sensor was basically hit, that, I mean, we didn't really specify a time, but I guess the perpendicular directions would have to change to yellow first. So like, assuming you come up to the stoplight, it's red
Okay.
for you. The
So
other
I
directions-
arrive and it's red.
You arrive and it's red. The other direction is green. That would need to change to yellow first, and then red, and then you would get a green and be able to go.
Okay.
That's sort of how we thought about it as a group. You're arriving at like a red.
Yep.
stoplight.
Okay.
Or,
Is that what we got?
that's for like, and then that's like the same concept we had for each light. And then we decided to just have the walk lights be, once a button is pressed, it's sort of added to the queue. And whenever the next red light comes
What?
around.
All right. So wait, let's go back to our. All right. So let's say this is the current state. So this is on. Right. So there's no zeros and everything else is a zero. Right. And let's just not even worry about the walk part of it right now. Let's just worry about the drive part of it. So this is our state. And I'm in the eastbound lane. And I drive up and I trigger the sensor. So this is our state. And all of these are also zero, right?
Yes.
Walk this car sensor. And so when I'm running my program, I go through, everything is happy.
Yeah.
Now I drive up, I'm an eastbound car. This becomes a 1. When this one becomes 1, you want the yellow, you want this to become 1. This to become 0.
So,
This to become 1, 0. And everything else stays the same.
yes.
For
some
some time, right?
Yeah.
Start the timer.
For some time.
So what is the yellow delay usually? 3 seconds? It's long enough to go,
Yeah.
right? It's definitely long enough to floor it.
Right.
I stopped at one yesterday, and the guy who was behind me, it was red when I stopped. It was not yellow when I stopped. The guy behind me pulls out and goes around through it in his big honking pickup truck. Probably had no insurance too. Just like the guy that hit my wife a couple weeks ago.
I mean, I think most of us can no longer count our fingers and toes because we don't see flashing red lights and all the rest of it.
The stop sign at Highland, not Highland, sorry, West and Institute. I saw a high-speed chase go through there. There was some guy in a little Subaru WRX. He comes flying through there about 60. There's a cop car coming right behind him, flying through at like 60. Gets up over the top of the hill. The car goes down the street, up. They went through that intersection like 3 times. I just watched. The police sirens from every direction. I don't think the kid was getting away. But okay. All right, so timer, whatever, 3 seconds. 3 seconds happens.
Your north and south would become 1s, and the north and south yellows would become 0s.
So,
Go back to
and
the state that we had.
Yep. Not the state we had before. I'm eastbound. Eastbound and down, loaded up and trucking.
Sorry.
I'm eastbound.
Yeah.
We just made
Yes.
north and south.
East green would be 1.
Right.
West green would be 1.
So 1. If this one is 1, then this one has to be 1.
0.
And those have to be, everything else has to be a 0, right? Right, because the timer ran out.
And then south and north reds would be ones.
Oh, south and north reds, right. All right. And then you'd have the same logic for each of the directions.
Yep.
Right. Yep.
We were ignoring the special cases. Could you just combine like the north and south lights in one output, and the east and the west output?
Well, each output is its own. But we can say every time that the north light is on, the south light is on.
Yeah.
Right. So that's a line of logic code in the thing. So we could control north and east and have south and west just follow north and east. But we'd have to control north when somebody is southbound or northbound. Right.
Same inputs, but
Yeah.
okay.
So you keep the same inputs and do that. Yep.
I just want to add that what you want to have a delay between when the green light goes on versus when like the other light turns red. Because some of the people that see the light. So
But I think if you observe the lights, that's rare. There's rarely a delay. It could happen, right? And that would be a better way to program it, right? So all right. So we could add a timer where all the lights are red for a moment. What else? So there'd be certainly some special cases to figure out with the ambulance signal, right?
We decided not to talk about this.
Yeah.
We didn't get into that.
They have a big brush card in the front anyway.
Yeah.
Just push those cars right out of the way. So do you have a little bit of feeling about the complexity of setting one of these things up? Now, could you imagine doing it with relays and wires as opposed to a computer program?
I probably couldn't do it.
Because right now, the way it works is you run a wire. I mean, obviously, you got to have a power wire to each lamp to turn it on, right? And you got to have wires that go to the sensors, but they all wire into labeled inputs and outputs on the board. And then if you decide you want to add in that delay, you do it in software. You don't have to go add a new timer to the board, right? If you decide you want to add in the ambulance stuff, you got to add one sensor that's going to get the signal, and it's probably going to have actual information in the signal, right? It's got to have to know the direction of travel of the ambulance. But that's fine because you can, with PLCs, with microcomputers, you can pass that kind of information along, right? You can pass along text. You could also have an output on here that's sending information back to home base that's telling somebody in the city control center what the condition of this light is. Right? What's the current condition of this light? And you may be able to even control them remotely. You've seen it in the hacker movies, right? They make all the lights turn red or green at the right time. Yeah. So in order to be that kind of hacker, you have to be able to do PLC programming, not just hack into computers. Think about that. All right. Are we good? What about no class on Thursday, huh? Ain't no class on Thursday this week. What's that? If we have updates that we want to give, let's do it. We got a few minutes. What's the status of the mold?
I don't think it has been machine yet.
You don't think it has been molded yet? What's the holdup?
Just getting it to the shop, getting it to the machine. We had it stocked, we had it code.
Okay. We are open during Wellness Day, but don't wait that long. You're on the 4-axis part, right? No, you're on the 4-axis. There's no 4-axis people here? Huh. Look at them. They must be in the shop machining.
I can't speak to it directly, but my roommate is on that group, and he said, or the mill group, and he said that Rodrigo wasn't there on Friday, he was sick, which he was sick, I tried to talk to him too.
He was.
That held him up.
He is there now.
Okay.
So they may have arranged to go meet him now. I don't know.
That was the last I heard. That was last week. They were waiting for.
And how about you guys? What's the next step?
Although we have our file ready to go for our second sample one.
Okay.
So we're trying to do that right now after class. And then if that goes as smoothly as it's supposed to, then presumably we can make our final part. And we still don't actually test making the X.
Have you got a program for the X? Okay.
We don't have to, I don't know the, I don't know how to get to the tool. So I can't, write it. But we just let this go up.
Okay.
So all we managed to have, all we managed to have for our second version of test prep is, so honestly, the only thing that is missing is the X. And we have like the clearance for the threads. I mean,
Mhm. Yeah, I mean, running the die over to make the threads, that's easy. For you guys, so the lab there's people there that can help on Wednesday during the morning time, for sure. And Friday all day long, and Thursday this week. Which day is advising day? Which day is wellness day? Thursday's advising day. Friday's wellness day, and we're going to be there both days. So so that works. Same thing for you guys. I don't know if there's anybody there to help you today. Did you arrange for somebody to be there to meet you? Because the lab's not open on Mondays until 1:00. So the one time we did it on Monday was because we arranged it in advance to have Thomas meet you. And when I was just there, I didn't see Thomas. So I'm not sure that there's anybody there that could help you.
Assuming that
Okay. If you, yeah, and so you're going to use the same lathe you used last time? Like it was number 2 or 1, 2? Yeah. So it should be okay if you get set up and you know how to do that. Rodrigo is around, but Joel is out today. And I have a meeting that starts at 11. So I can help you up until 11. All right. Sweet. Let's go.